Okay, one more thing that we want to talk about for today's lesson is potential energy diagrams. There's a few different names for these, but that's a really common one, a potential energy diagram. It's a way of showing potential energy as it changes in terms of a graph, and it gives us a lot of information related to enthalpy of reaction and so on. The enthalpy of reaction, again, this is just a reminder from what we learned already today, is the change in enthalpy of the reaction. And the way that you determine it is by subtracting the enthalpy of products minus the enthalpy of the reactants. Okay, now the activation energy is the minimum amount of energy that's needed for the reaction to happen. That's a new vocab term. Activation energy is the minimum amount of energy that's needed for the reaction to happen. We talked about this for just a little bit when we talked about rates of reaction and what makes reactions happen faster, and we mentioned a catalyst. A catalyst provides a lower pathway, a lower energy pathway for the reaction. In other words, it lowers the activation energy. The amount of energy that's needed to make the reaction happen. That's another way of thinking of it. The amount of energy needed to jumpstart the reaction, to get it going. Well, here's how you calculate it. Activation energy is the top of the hump minus the enthalpy of reactants. Looking at our diagram down here will make sense of that. But when I say the top, I mean the very, very highest point on our potential energy diagram. We're going to get into that now. All right, start with enthalpy of a reaction. For an endothermic reaction, the heat for an endothermic reaction is going to be absorbed by the system. That should be review at this point. Heat is absorbed by the system. That means that heat is going to be on the reactant side. Heat goes into the system. It requires heat. If enthalpy of reactants, if we're talking about enthalpy of reactants for an endothermic reaction, that is going to be lower than the enthalpy of the products because heat has to go into it to make it happen. So delta H of reaction, just like Q, delta H of the reaction is going to be positive. The temperature of the surroundings for an endothermic reaction, temperature of the surroundings will decrease, which means the solution will get colder. Now let's look at our diagram here. I want you to notice a few things. You've got a curve, and what happens is as the reaction takes place, that's what reaction progress means, as the reaction takes place and reactants are converted into products, a certain amount of energy has to go into the reaction. And if it's endothermic, then overall the change from the very beginning to the very end is going to be an increase. It's going to be a positive change. So delta H is positive. That's an endothermic reaction. If you look at the exothermic reaction, you see how we've got an arrow pointing down. That's because in this reaction, and we'll come back to this, delta H is negative. Heat is being released by the system. That's why the potential energy diagram, the reactants to the products, there's an overall drop. Okay, now let's look at a few things here. This jump in energy at the very beginning, we have to get over the top of this hill in order for the reaction to take place. So that arrow that we have there, that red arrow, represents what we call the activation energy. The activation energy is the amount of energy required for the reaction to happen. Whether it's endothermic or exothermic, we have to have the activation energy. A certain amount has to be put in to make the reaction happen. Once you get over that hill, the energy will start to drop again. If it's an endothermic reaction, it still won't drop all the way back down to the level it was before, but it'll drop part way until we get to the energy of our products. That's where we get this enthalpy of reaction. That's the value that is the difference between here and here, where the reactance level is. And if we had this labeled over here on the y-axis, if we had numbers labeled, we could actually calculate that. Okay, let's look at the exothermic reaction. With an exothermic reaction, heat is released by the system. Heat is going to be on the product side. The enthalpy of the reactants is going to be higher than the enthalpy of the products, which is the opposite of what we said for endothermic again. And delta H of the reaction is going to be negative. We have an overall decrease in potential energy. The temperature of the surroundings in this case will increase because it is releasing heat to the surroundings. The solution will get hotter. And if you look at this diagram as it compares to the other one, it looks similar in some ways, but you can see that our reactants have higher energy than the products do. So it's flipped in that way. As the reaction proceeds, we still have to get over that activation energy bump. But then afterward, you can see that the reaction's potential energy continues to decrease until it levels off where the products are, and the product's enthalpy is lower than the enthalpy of the reactants. That's how we know that this is an exothermic reaction, based on the shape of the diagram. So if you are answering questions where it just simply asks you, is this an endothermic or exothermic reaction, you can look at the shape. Something like this, where you've got a lower energy becoming a higher energy, that's endothermic because energy is being absorbed by the system. There's an increase in enthalpy. Delta H is positive. And then if you have something that looks like this, where your starting energy is higher than your ending energy, that's exothermic because delta H is negative. That's pretty much a summary of what we just looked at, what we just talked about here. I might do a short video to introduce the practice problems that are related to it. Then try your hand at them, and you can check the video if you need a little bit of help.